Hey everyone, our next step in our rotation unit is going to cover Newton's second law. If you remember from first semester, Newton's second law was F equals ma, or more properly written as A is equal to F over m, because it really is a force that causes an acceleration, which can be hindered by the amount of mass an object might have. Also, what I want you to keep in mind is that the force that we were talking about was actually the net force, the sum of all of the forces that were acting on the object. Well, if you remember, everything that we've done so far linearly had a rotational counterpart. Force has a rotational counterpart in torque, and that is equal to mass's rotational counterpart. And if you remember, mass is really just a measure of inertia, right? They're related. So our rotational counterpart for mass is our rotational inertia, and our rotational counterpart for acceleration is alpha, meaning our new Newton's second law equation, as opposed to F is equal to ma, is now torque is equal to I alpha, or more properly written as A is equal to torque over rotational inertia. What this does is it allows us to see the relationship between these two variables, torque and rotational inertia, and the relationship with alpha. As we can see, just like with Newton's second law of linear motion, our equation showed us that if torque would go up, if the force would go up, the amount an object would accelerate goes up as well. The harder we push something, the more it's going to accelerate, and vice versa. Showing that force and acceleration had a direct relationship. Because mass is in the denominator of the equation, if mass were to go up, the amount of acceleration goes down. Again, the opposite is true. If mass were to go down, our acceleration would go up, showing that these two variables have an inverse relationship. Showing the same thing with our Newton's second law of rotational motion. If we look at the relationships between torque and alpha, and I and alpha, or rotational inertia and alpha, if torque were to go up, then alpha would go up. Likewise, if torque were to go down, alpha would also go down, showing once again that these two have a direct relationship. And just like with Newton's second law of linear motion and Newton's second law of rotational motion, if our rotational inertia goes up, our alpha were to go down, and if our rotational inertia were to go down, our alpha goes up. Showing again, just like in linear, they have an inverse relationship. Right, just like linear. And if an object has more mass, more resistance to change, its acceleration will be less when it's pushed on. Rotationally, if an object has more rotational inertia or more resistance to rotational change, its acceleration is going to go down when acted upon by a torque. Again, one of the things that I want you to keep in mind is that we are talking about the net torque in all of these, just like we were talking about the net force when we were dealing linearly. When it comes to a graph, if you remember, having a force versus acceleration graph would give us the mass when we would calculate that slope, right? Our slope would be our rise over our run, meaning our F over our A, right? Rearranging our equation, mass would be equal to force over acceleration. When we look at a torque versus alpha graph, if we were to calculate the slope of that, doing our rise over our run, we get torque over alpha, which is going to be equal to our rotational inertia. What I want to do is I want to take a moment to look at the units in this, right? Our torque is measured in Newton meters, and our alpha is measured in, radians per second. But I also want you to remember that that newtons are actually measured is actually a kilogram meter per second squared. Sorry, and I said radians per second for alpha is radians per second squared. So kilogram meter per second squared over a radian per second squared, which is really just a kilogram meter per second squared. If I multiply by the inverse, that's a second squared over a radian. My second squared cancel out. I forgot my meters there. Now, what happens to the radians? Well, we don't really need to know this or cover this, but really, a radian is really just the ratio between arc length and radius. Both of those measured in meters, which means radians is really unitless. So when I'm measuring units, I can actually just kind of get rid of that, which means I'm left with a kilogram meter times a meter, or a kilogram meter squared, which we know is our unit for I. Right? So that shows me that by taking the slope of a torque versus alpha graph, I can calculate my I value. Just one more way to be able to calculate, one more relationship between our linear and our rotational counterparts. What I wanted to do was take a second to practice one of these problems. We're going to jump down here. This is page 29 in your packet. It's a little off because I added a couple of pages in here for these notes, but we're going to look at number 4 here. A 30 centimeter diameter wheel with a moment of inertia of 10 kilograms meters squared is rotating counterclockwise at 6 radians per second. Then a brake is applied as shown. If the brake is applied for 2 seconds, the wheel is then rotating at 0.5 radians per second. What force did the brake apply to the wheel? Well, the first thing we want to do here is copy down our givens. We know that we have a diameter of 30 centimeters, which really means that we have a radius of 15 centimeters or 0.15 meters. We have a moment of inertia. Remember, moment of inertia is just another way of saying rotational inertia of 10 kilograms meters squared. We've got a counterclockwise velocity, rotational velocity of 6 radians per second. That's going to be my omega 0, because I'm going counterclockwise, remember counterclockwise is positive, so 6 radians per second. I have a time of 2 seconds, and I have a final omega of 0.5 radians per second. And ultimately it wants to know what the force is. Right, there's my question mark. What is my force? If you remember going back to linear relationships, when we covered Newton's second law, that F net is equal to ma, we had a lot of combo problems that were a combination of force and kinematics. And if you remember that Newton's second law, that F equals ma, was our bridge between Newton's laws and our kinematics. And the reason for that, we'll get rid of that guy. The reason is that equation of F equals ma. It has that acceleration aspect, right? So it's going to be our bridge between anything kinematics that used our velocities, our distances, and our accelerations, and our forces. It's going to be the same here. We're going to use our rotational counterpart of this, of torque is equal to I alpha, to be our bridge between anything kinematics and anything that is torque or force related. So my first step is, since I'm given a bunch of stuff in kinematics, right, our omega 0, our time, and our omega, is I'm going to solve for my alpha using kinematics. And I have omega 0, time, and omega. I need alpha, right? That's going to be my shovel equation of alpha is equal to, I'm rearranging here, omega minus omega 0 over time, or 0.5 minus 6 over my 2 seconds, right? 0.5 minus 6 is going to give me a negative 5.5 divided by my 2 seconds, or my alpha is going to be negative 2.75 radians per second squared. Now that I have my alpha, and don't forget I already had my I value, using my equation of torque is equal to I alpha, I can use those two to go ahead and calculate my torque, which I'm ultimately going to end up using to solve for my force, right? So if my torque is equal to I alpha, my torque is going to be 10 times my negative 2.75, or my torque is equal to negative 27.5 Newton meters. Remember, what I'm actually looking for is my force, right? Force is my ultimate goal here. Well, I also know that torque is equal to force times my radial distance. With everything being perpendicular on here, I don't have to worry about any angles. So I'm going to take my torque, I'm going to divide it by my radial distance, and that's going to be equal to my F, which is equal to my torque of negative 27.5 Newton meters, divided by my radial distance of 0.15 meters. Remember, we had to convert that into our diameter into radius and into meters. And if I pull out my calculator here, I get my 27.5 divided by 0.15, and that gives me a force of 183.3 newtons. And there we have it. Again, linking this back to linear, our ultimate connection, our bridge between our kinematics and our torque and forces is going to be that Newton's second law. Newton's second law of torque is equal to I alpha is how we're going to move between anything kinematics of, our rotational kinematics where we have omega 0 and omega or delta theta, and our forces and our torques. Hopefully this will help you move through some of the other problems on here. If you have any questions, always feel free to contact myself or Mrs. Fine-Ice. As always, Mrs. Fine-Ice is in the ARC during first hour, and I am in the ARC during fourth hour. Please feel free and to drop by and say hi to either one of us if you've got any questions. Good luck.